I'm going to be brave and try and stand up through this. So one of the questions you're not allowed to ask at the end is what happened and why I've got a bad knee. I got hit by a taxi. It's a fun story. For another time, maybe at dinner. Okay, so the title of my talk was Fragalysis, an open source web platform in the cloud for reviewing and progressing fragment hits from the beamline. But we changed the story in the car on the way home from work about 2 days ago. So a better title for my talk is why looking at loads of ligand structures in PyMol is crap, how we should look at them differently, and what we can learn. Frank tried to make me change the title, but I wanted to say the word crap in front of lots of people, so it sticks. Okay, so just a quick outline of what I'll talk about. I'll give you guys a brief intro to fragment-based drug discovery, just in case anyone's forgotten what it is or didn't know. I'll talk through our experiment just to give it a bit more context. I'll tell you why looking at loads of structures in PyMol is crap. And I'll tell you what we should do to make it better, and tell you a little bit about ensemble-based drug design. And then I will show you what Fragalysis is, so you've got a bit more context about what we're doing and how we're trying to solve this problem. So fragment-based drug discovery, the idea is you have small libraries of small molecules, so they're typically less than 20 heavy atoms. The number of fragments in these libraries is generally much smaller than high-throughput screening libraries that contain drug-like molecules. Larger molecules do have more possible interactions that they can form with a target, but they're not always favorable interactions. So that's kind of shown up the top there by that big red molecule not really fitting where it should in the target. So smaller molecules tend to have fewer opportunities for interactions, but because of that, they bind more easily and you tend to get more hits from a fragment screening experiment. And the good thing about them is they do lots of useful things, like they help us uncover structural insights, but they are generally very weak affinity in terms of their binding. So then to get more toward a drug, what you want to do is optimize those initial hits with some medicinal chemistry. So at Diamond, we have the XChem facility. So it's a fragment screening experiment directly into crystals, where we soak one compound into one crystal. And the soaking, the harvesting of all the crystals, the data collection, and all of the data processing is nice and streamlined now. No thanks to me, thanks to all of the awesome Beamline people at Diamond. And they can now screen about 1,000 crystals a week, which is pretty cool. They've had routine users since 2016. They managed to do about 125,000 crystals in 3 years and got over 3,000 hits for over 130 targets. So this is just a quick example of a typical output from a fragment screener XChem. This is actually one of our PhD students at the SGCs, targets Yulia, who's somewhere in the audience. I can't see because the light is very bright. So what you tend to get is a big cluster of fragment hits, usually in the binding site where you'd expect them to be, and then a few other fragments around the protein, and they could be in cryptic pockets, they could be in allosteric sites, or they could be at contacts, for example. So the problem then becomes, what do we do with this mess? Because we've got loads and loads of structures and data, and we want to get a drug. So what do we do? Most importantly, we want to know what we can make, usually fast and cheaply, because a lot of our users are academic groups who don't have massive amounts of funding like pharma companies. And we want to know what we should make as well, not just what we can make. It's useless just making everything we can without any knowledge of whether it's going to work or not. So will it look like the drug we want? So will it actually penetrate? Will it be soluble, etc.? And how can we actually use all of that information, not just to get a drug, but to learn other things about our target maybe? So this is the slide on why looking at loads of fragment hits in PyMol is crap. Maybe it's just because I don't use PyMol that often, because I write a lot of code. But to me, that doesn't look like a good way of looking at loads of fragment hits. You can't observe any patterns. You can't look at subtle differences in different conformations in the bound state. So these tools really, they're designed in a way that you can only ever evaluate a few structures at a time. And they don't identify and highlight those trends that you want to look for in data sets to inform structure-based drug discovery. So the idea of ensemble drug discovery is using all of the structures and all of the knowledge you get from an experiment like this with hundreds or thousands of crystal structures to inform your structural-based drug discovery in a more objective way. Because using software like this, it's repetitive, there's a lot of manual work, you have to rely on the scientist remembering the patterns they've seen in structures before, and it's incomplete and subjective, basically. So a guy called Anthony Bradley, who did work with us and left us to work for Excentia, damn him, came up with a bit of software during his PhD called Wonka. He also did his PhD in Frank's group. And the idea of Wonka was to move towards objective analysis of multi-protein ligand structures, so an ensemble of protein ligand structures. And a couple of features he included in that were pharmacophore formation and ligand fragmentation, feature clustering, so looking at features in the protein or the ligands over multiple structures, and also how you should visualize these things as well. So I'll just go through a couple examples of those. So this example here is taken from his paper. So on the left on your side and my side is that mess I'm talking about, where you've just got all of the structures overlaid together and you can't really tell what's going on. On the right-hand side is what Wonka will show you. So up at the top, where they're colored in yellow and purple, you've got clusters of conformations of a tyrosine, and you can click on those different clusters and see which ligands cause a conformational change. So it allows you to see the pattern a lot more clearly. Another thing he thought about was waters. So again, on the left-hand side, the waters are all in blue. It's a bit of a mess. You can't really tell what's going on. On the right-hand side, he's clustered the waters together and represented the waters in the site with those red spheres. And the green thing that you can't see so well, each block represents a ligand, and where it's white, that's where a water isn't conserved. So you can immediately see which ligands displace those waters. And finally, this is a representation of how ligands fit pharmacophores. So if a pharmacophore isn't conserved, again, the block is in white. And another good thing about looking at proteins in an ensemble approach is it allows you to spot errors and other interesting things in your models. So Frank put a quote in my slide earlier, which is quite nice, which is that outliers are either errors or interesting. And then on the right-hand side is an example randomly pulled from Google today, where they're using ensembles and have worked out what the major and minor conformations of a residue are. And then obviously if you've got a model where you don't fit that one of those conformations very well, you might have an error or you might have something really interesting going on. So yeah, and those sorts of studies are often complemented by things like MD analyses. So now just moving on a little bit towards what I'm doing and what we're doing at Diamond with follow-up chemistry. So this is just to give you a bit of context of what we do after we've got that data and we've got our models. So we need to triage our original hits and decide what we want to follow up on and filter by either structural or ligand-based hypotheses to improve the potency of follow-up compounds. Then we need to actually find some compounds that we can make or synthesize. So we need to enumerate a library to decide how we should modify those triaged hits and make sure that we're enumerating in a way that we try to align with the hypotheses we've generated. Then after that, we need to validate that those compounds we've picked actually do align with those hypotheses and score them in some way. So we have a nice prototype at Diamond, and actually we know that even for users that don't come and use a big facility like Diamond, the idea of curating this massive data is quite overwhelming. So we want to sort of bring that paradigm into the cloud, and the reason for that is because it's much more accessible to have things in the cloud than have hefty software packages that don't always get updated and things like that. So you can read this if you want to, but the main message is our aim is to move data into the cloud for analysis and provide robust and accurate and accessible tools for people to use. So that's why we designed Fragalysis. This is a picture of what's currently the production version of Fragalisis, and this was our alpha release. So the front-end developer at the time made us a very nice cake, and that's not a fish, it's an alpha. We do currently have a much prettier version, which makes me very happy. It's currently the development version because there are still a few bugs to iron out. I don't want to say too much about Fragalysis because I think the take-home message is more about you should be looking at your proteins in a different way to get a better idea of what's going on, and looking at lots of structures all at the same time will inform you a lot more than just navigating through them in PyMol or whatever. So go and have a look at it and play with it, and let us know what you think. The overall goal for Fragalysis in the long term is to have this cloud stack, like I say. So what we've already got, please work. That's my hand not working. Okay, that doesn't work because I don't know how to use it probably. So I'll use what we call the Von Delft pointer. We already have a web UI, which is quite nice. But we need to have a more robust system that's expandable and accessible to people. And we really need to bring in drill down workflows for picking those follow-up compounds, which involves running lots of calculations. So we need a link to HPC as well, which we're almost ready to link up, which is really exciting. And obviously the overall goal is to have compound purchasing and access to synthesis plans as well at the end, so people can actually make use of data that's there and algorithms they can run to bring things back into the beamline and run more experiments and get those more potent compounds. So the status of that project at the minute and a bit more ambition, Janssen have funded a big burst of development for the next year, and our #1 priority is to make it deployable so anyone can deploy it in-house if they want to, or pharma companies can use it, whatever. We're all about open science as well, so everything's all on GitHub. And we hope to have that achieved by the middle of this year, I think. That might be ambitious, I don't know. You can ask our actual coders. And then afterwards, that link from Fragalysis to HPC and different drill down workflows will be our priority. The other wonderful thing we've got is a bunch of 5 students through the DTC at Oxford, which Frank calls the Fragment-5, which is an awesome name for them. And they're awesome kids as well. So they're writing an API for Fragalysis, and the point of having that is because we want these algorithms for data manipulation, analysis, and evaluation to be available to the wider community, and make sure that within reason people can have access to cloud resource as well through the API. So the things that they've managed to do between September last year and now is write some algorithms for preparing data so that it's suitable for something like Fragalysis. So things like aligning multiple PDB files and pulling ligands out from the PDB file. And then after that, we want to expand a bit and have the ability to add data to Fragalysis from the command line and evaluate data with the Wonka algorithms, query for new follow-up compounds, and estimate 3D structures of ligands based on initial hits. So Frank's group is massive, so there's loads of acknowledgements. The most important people are over on the right-hand side, so the Fragment-5 for the API, Anthony Bradley for coming up with the idea, Rick for making an awesome cake and being our front-end developer for a while, and Tim and Alan for maintaining our cloud infrastructure. Thank you. And I'm still standing, so we're doing well.
Okay, thank you, Rachel. I'm sure there will be questions about fragment analysis. There's one.
If I may, you mentioned PyMol, but you didn't mention Coot. Coot has a Wonka clone in it. I wonder whether you're familiar with that.
I'm not a crystallographer either, so not really. I think some of the guys in our group might be, but I rarely even look at structures because I'm a computational chemist, so I just write loads of code all the time.
Well, if you're writing APIs for Fragalisis, I would appreciate a Python-based desktop client version.
Okay, awesome. The API is Python-based as well, if that's useful.
Thanks for that. That was great. An XChem is great. How are you dealing with structures where you kind of done an XChem, you have different crystal forms accidentally in there, and like 4 molecules, say, in the asymmetric unit and different fragments? Is that all going to be handled automatically?
So that's a difficult problem. So the curation pipelines that we have at the minute, I don't think I've actually written anything in there to think about different crystal forms, and Fragalysis doesn't do anything about it either. But it doesn't allow you to expand the lattice or anything, so we just align based on one asymmetric unit usually. But you do get weird cases sometimes in Fragalysis where you have two copies of the protein in there because there's a different crystal form, I assume, which is something we need to sort out, I guess. But it's working out whether sometimes there are two different conformations of the protein in some forms and just one in other forms and things like that. So it's something we need to think about, definitely.
I have questions, please. What technology is used to program Fragalysis? Directly HTML and JavaScript, or something that translates to JavaScript and HTML?
So it's JavaScript, and it's a React Redux framework so that we can save state and things as well. Because another thing we thought about that was very important was the need to be able to collaborate on projects like this. So Fragalysis has the ability to save sessions and to share snapshots of what you've done on the interface. So you can send someone a link and they'll load up the page and it'll look exactly how you left it. And that's something that's only enabled through React and Redux, I think. The database and stuff is all Django. So there's a bit of Python involved as well.
Okay, if there's no other questions, let's thank all the speakers again.